Wow. OK. Wow, that's going to be hard. So, about me. I work as a software architect for Spill Games. Spill Games, you might have heard of them. We're a company that is one of the main game publishers. We do casual online gaming and also social gaming. We have web portals with strong domains all over the world, like agame.com or gamesgames.com. Those are a couple of English websites. My role involves basically overseeing the landscape, technical landscape of the company, and also coding on a daily basis and prioritizing tasks. So that's what I do. What I won't be talking about today is client-side caching, caching proxies, and CDNs. And the reason is, first, I'm not an expert on that. And second, that doesn't play a relevant role in the performance of our websites. So one of the key things in the portals that I'm going to present today, or the architecture behind them, is that we generate full HTML pages in the backend, which means there's no HTML caching involved. There's no serving a template of HTML and then letting JavaScript run to generate the dynamic content. We serve fully backend generated pages, personalized for every user based on information we get from Data Warehouse. Even if you're a guest user and you come to our portal, after 5 minutes of play, we can actually provide you with a specific recommended list based on what you have done and this kind of things. And all of that is backend generated. So this is one of the portals. As you can see, there are some recommendations and links to games everywhere. Well, that's basically what we do. And how we do business is, yeah, the text is not very readable. But so basically, we have a catalog of games, which is in that purple bubble over there. This one. Yeah. We have our own studio providing games, but we also get, actually, we get most of the games from external game developers. And we have an advertisement solution that allows us to hook different ad networks to our system. We package a game together with in-game advertisement in a ball, and we can serve that ball from all of our portals. And we can also put it in the app stores and serve it to external publishers, etc. So we have a rounded, packed solution that we just serve to the outside. And I'm not going to present today the web framework that we use to build the portals. I did that at the Erlang DC in December. I also did that at Erlang User Conference last year. So today is about what's behind the web, behind the framework, all those APIs and all that business logic that provides us with those recommendation lists, for example. And that's actually a 3 layers architecture. So the first one is the interface layer on top. It's responsible for load regulation and type validation. So making sure every request you make to our backend is actually correct, and every piece of information that we serve is compliant with the APIs that we offer. The bottom layer is the storage layer. It's a distributed storage. It's also Erlang. All the layers that you see there are purely Erlang. I presented that one last year here in San Francisco. And in the middle, we have blocks providing the business logic to actually gather the data and format it, etc. So for example, you can imagine a request to interface game on the top right of the picture would involve actually checking what user is making the request and retrieving a list of game IDs that are especially relevant for that person, and then going to the service game on the right of the middle layer to retrieve all the information for those IDs, and then the interface on top aggregates all that information and pass it up, ensuring it has the valid format. So that's basically how we work. And what's actually the role of caching in all these? Well, first of all, we cache for performance. That's kind of an easy one. So memory is cheaper than network I/O, and memory is cheaper than database accesses and maintaining pools of connections and these kind of things. So that's kind of the first reason to cache, right? It's because you want to go fast. The second one is caching can act as a safety net for you. And this is especially interesting. I will be showing in the end of the talk a nice story about how caching actually made us through the weekend when we were actually having issues. There are certain considerations that you really need to have in mind when you do caching. So on the left side, you can see the horrible waves of traffic that are actually getting to your data center and your systems. On the right side, you can see your systems. So caching sits in the middle, which means if you heavily depend on it, the moment your caching is gone, your systems will be destroyed. And you can think like, yeah, it's never going to happen. You know, I will implement a very solid caching solution and it will be fine. But it will not. There are many scenarios that can actually cause that barrier to disappear, starting with just a deployment and cold start cache misses. You know, if you cannot really handle the load, you're done. You can have a developer just flashing a cache to see what happens. You can have an architecture based on 7 levels of cache and then 1 backward incompatible change, and then you have to start flashing them and pray. Yeah, so there are many scenarios that are actually very prejudicial. So caching is great to optimize. Caching is good, but do it once, do it right, and do not depend on it. Yeah? So basically, what we're trying to do here is caching only in one place, as close as to the data source as possible to improve the performance and to avoid issues with updates and cold starts and these kind of things. Considerations when choosing a caching system are diverse. One of the most interesting ones is distribution versus replication. So depending on the size of my data set, I might desperately need to have a distributed caching system that uses some consistent hashing algorithm and then having some part of the key space in some servers, some other parts in other servers, and see how to go from there. Maybe actually your data set is small, and you can just cache it in each and every one of the nodes, which is better, because then if you lose a node, all the information is cached in all the rest. So it really depends what you're going to do. The other thing that you have to consider is how long will the validity of your entries be, and what kind of granularity you need on eviction. So do you really need very fine-grained memory control? Like what happens if you have a couple of entries that are no longer valid but are still using space in your memory? Well, if they are tiny and you have plenty of memory, it's not really a problem. You shouldn't probably hurt your performance by making sure they are actually evicted at the right time. On the other hand, if you have, like, I don't know, huge entries and they are not in use, you're just wasting your memory. So it's a balance. The other consideration that's particularly interesting when you start playing with caching business logic, so, or caching to avoid expensive calculations in your business logic, is what to do with an error. Meaning, I'm caching this particular piece of logic that creates or calculates something that's really, really very heavy, like think about a cubical or a quadratic loop with a very long input, and it generates an error. So what do? You cache it. Well, then all your users are seeing that error even after your system has recovered, right? OK, fine. So we don't cache it. Well, what happens if it's actually an overload error? Particularly on a web stack, right? So user sees the error, you don't cache it or remove the entry from the cache, user hits F5, multiply that by 200 million users that we have. Nice, yeah? So that's exactly what you don't want to do. So you have to think about it. Yes, you probably want to cache the error somehow, but you need to find a proper balance for your business. So today I have two different proposals for you. There are two open source libraries that we want to release to the community. And both of them are tested in real fire. So I didn't mention the numbers before, but so we have 200 million unique users a month, and we also have like 120 gigabytes of data being stored in our data warehouse systems on a daily basis. So it's big. It's real traffic. Okay. So both solutions have been tested, and I have graphs to show you the stuff. They're different. So the first one is actually a combination between Memcached and a library that we're open sourcing that's called AirMemcache. So Memcached, I don't know how many of you actually have worked with Memcached or so, but it's very famous as a nice performant implementation of a cache server. It's actually the reason behind lots of LAMP stack applications being able to support real traffic. Yeah, so it's actually the secret that everybody knows is needed. Yeah. It's good if you don't want to reinvent the wheel, creating a complex caching server. It's high performant, written in C. It allows you to do distributed caching easily, because you can just put a Moxie in front and then just Moxie takes care of the consistent hashing and distributes the keys, which is simple and nice. You don't have to do really any magic at all. And of course, your system administrations will love you because they have been working with this for a long, long time. So nothing new to learn, no new technologies. It's not the airline guy coming up with crazy ideas again. You know, this we know, this we can manage. So there are scenarios for it. How does this work? Well, again, it relies on Memcached. So this is not a caching server, it's only the client. Yeah? It implements a pool of TCP connections, and each one of those implements the Memcached binary protocol. This is interesting because it's fast. That's the key, so it's fast. And it allows you very fine-grained memory management. That's something that you can do very well with Memcache, and is actually heavily tested. And the most beautiful functionality of this system, in my opinion, is that, well, of course, it survives a node restart because the cache server is out of the node. So if you have to do a deployment, maybe your cache is still valid. You don't have to flash it or anything like that. But if you're running the Memcached server locally together with your Erlang node using the library, Erlang can actually supervise your Memcached server and restart it if needed. And that's actually quite interesting. I won't call it rudimentary, but basically the system works by inferring the health of the Memcached server by the health of the pool that's connected to it. So if you have many connections to the pool that are dying because they cannot reach Memcached, and Memcached is running locally on a port, it will actually try to restart it. It is that simple. So you lose the information, but your pool gets regenerated, everything is healthy, and you can keep using your system. And it's actually done with a supervisor, so it's actually quite cool. You can more or less see how it works. On the green balls are supervisor. The main one is the application supervisor. The other one is a pool supervisor. So the ball on top is the user interface module, which is called Memcache. You just have get, set, etc. as usual. And the supervisor below holds the different pools of connections that might be pointing out anywhere. So one of the pools can be pointing to a local port when you have Memcached server running. The other pool can actually be pointing to a different machine, to a Moxie distributor layer. You can actually use the library however you want. So this is one of the options. The other option, yeah, before we get to the other option, the other thing is, I said this was tested in RealFire, so this is actually how we do caching for the Spill Games storage system that I presented last year, which is kind of an abstraction on top of the storage. Below it, you can use React, or you can use MySQL, or Postgres, or Swift, or whatever kind of database that you want. So the storage is storage engine independent, but it performs data validation, and the distribution is already taken care. That's, yeah. So it's quite a nice storage system. But of course, the key is you don't always want to use to access disk for every entry, or to go to the database that you are running behind for every entry. So this application automatically uses Erlang Memcache to keep the caching separated and being able to have a fine-grained control, and it allows you to do optimistic operations that operate in memory first just by actually using this library. So there you have a real use case, and that's the URL of the repo in the case you want to take a look. And now the other option is ErlCache. And ErlCache is a very simple caching application that works like a server of caching servers. So it's great for in-node caching of small data sets. So I don't know if there's anybody from Klarna on the room, but given the numbers that Kosti showed in the previous talk, yeah, this is not for those guys. Really not for you, don't do that. But this is actually nice for caching outside of the node, inside the node. When you have small data set, it allows you lots of concurrency, and your data can live there for quite a long time. The caching strategies are not to be set by server, like validity and eviction and these kind of things. You can set defaults per caching server, but you can actually, within the same caching server, specify different parameters per key, which gives you a lot of control. The application is error aware, so it will apply different strategies when dealing with errors, when finding an error when trying to cache a value. And it allows you to do non-intrusive memoization of your code. So I don't know if you're familiar with the concept. It's something that's very popular in the Clojure nowadays. So basically, transparently cache the result of your function for future reference. Yeah, so this library allows you to do that in Erlang. The way it works, each one of the caching servers is a gen server, which holds a protected ETS table with read concurrency enabled. So it's optimized for massive lookups. Yeah, that's how it works. Each one of the cache servers also keeps track of the stats. The stats, of course, are calculated asynchronously, otherwise it would hit performance pretty badly. But still, stats are good enough to get a very nice overview of your system when you hook it to your monitoring. It implements periodic eviction, so careful with this, think about it. If you have long entries or so, if you want fine-grained memory control and you want entries to be evicted as soon as they expire, this is not good. Yeah? And it allows you to auto-refresh overdue entries. So what are those? Basically, the idea is that there are 3 stages for each one of the entries that you have. The entry can be valid, which means, OK, I have just calculated it. It's there. You will request it. You will get it back. Everything works. Everybody's happy. The entry can be overdue, which means, well, according to the validity terms that you specified, this has already expired. But also, you specified that you didn't want it to be evicted until it was this old. So there's this gray area in the middle that is overdue. And during that overdue, entries are automatically refreshed. And you can actually, whenever you hit with a GET request an overdue entry, you can specify or rely on the defaults that you have specified for your server, whether you will accept the overdue entry, and the refresh will happen out of line, or you want to wait until the entry is refreshed and get the most recent value, which gives you, again, a lot of flexibility. The API is very simple. So you can start a cache server by providing a name and a set of default options. You can stop it, of course. You can also configure a list of cache servers with default options in your config file, and the application will manage to do that for you. And then you have a get, a set, an evict, and a get stats. So the API is really simple. Now, the trick is the piece of code that you see below. So the last 3 lines is a very simple description of what you can do with this. So you have something that is an operation, receives an input, and performs some extra complicated calculation that involves database access and disk reading and TCP communication and whatever you want, and returns some output. And just by adding that tiny little line on top, saying, I want you to cache this in my caching server S1, and I want you to use these specific options for it, the macro will actually take care of trying to get the entry for the cache from the cache, and if the entry is not there, go and calculate the value, set it in the cache, give it back to you. And you can specify that, OK, I'll take the not found, or I'll take the value, I'll wait until you store it. All of that is normally specifiable by the options. So the idea is, per cache server, you can configure stuff like the validity time and the eviction time. Yeah, so if you specify validity is 5 minutes and eviction is 1 hour, that gives you 55 minutes of overdue, which means the entry will be auto-refreshed if it's hit. Yeah. You can specify a refresh callback. In the case of the macro you saw before, obviously the refresh callback is auto-generated and is a call to the same function with the same parameters that you actually called, which is quite nice. So if you basically place that macro on top of add x, y equals x plus y, when you add 1 and 2, and you try to add 1 and 2 again, you will retrieve the value from the cache. If you add 1 and 3, the value will be calculated and then cached. Yeah. You can specify whether you want to wait for refresh or not. So whether you will accept the overdue value as is, or you want to wait for the overdue value to be fully refreshed and then only get it when it's really valid. Yeah. You can specify whether set and evict operations should happen synchronously or asynchronously. Think about a case where you do a set, and immediately after you do a get on the same key. Yeah? Should you actually get what you have just set, or you don't care about that? Because if you don't care, then do it asynchronously, and the load in the system really decreases. You can specify what's an error for you. So the application by default will consider errors, anything that is in a tuple error comma something, or the atom error. And all the rest will be valid values. But you can specify it yourself. You can pass a callback, and then the application will try to validate every value before caching it, checking whether it's an error with that callback of yours. And of course, you can specify a specific error validity, meaning that, OK, I will cache entries for 5 hours unless they are errors. And if they are errors, I want you to cache them for only 3 minutes. And errors will never be auto-refreshed. Just to avoid, again, overload situations, if you have an error, the error will never be auto-refreshed. So errors are cached for a specific error validity, and then they are out of the cache. And then if you actually try to get the same value again, then it will try to retrieve it. And if it generates an error, we'll only cache it for, again, the error validity. So the application is very flexible. And again, a little bit on the structure is kind of the same. So the blue ball on top is EarlCache, which is the user interface module, which is the one offering the API that I showed you before. So start cache, stop cache, get, set, evict, and get stats. That module is responsible for providing you with the API functions and also storing the defaults for all the different cache servers that you might have and perform all the parameter validation. And that leaves us with EarlCache server module, and each one of them just implements the logic of caching. So it's assuming clean input because the input has already been cleaned. Each one of them, the EarlCache server holds the cache, which is the ETS table. And when using the interface, you read straight from the ETS table. And when writing to it, the writings are serialized through the Gen server. So what do we use this library for? We use it to avoid inline expensive calculations. We have some complex operations to retrieve relevant information for users. And sometimes they can take a while. And we use it to protect the application running the business logic, of course. And you can find a repository in there. And also it's open source. So I encourage you to try it and give us your feedback, whether you like it or not. So the idea behind this project was actually that at some point we found that in our code base there were like 13 or 14 different implementations of different subsets of this. And I bet you also have in your code base something like that. It's so simple. You implement a tiny Gen server, that holds some state and maybe a timer or two to change the values or whatever. And yeah, it's all over the place. And it's one common pattern that actually fits the bill. You just have to configure it properly. It's easier to maintain. You can test it properly. For us, it had really great value. So is the line visible? Can you see the line, more or less? OK. So in this case, I'm going to tell you a story about the get-related labels call. And that call is responsible for getting labels that are relevant for games based on the labels of that game. So you have an action game. Give me labels that are more often related to action, like racing or shooting. Yeah? So that's an expensive calculation. We're talking about thousands of games with 10 labels, 20 labels each game, and you have to actually cross all that data. So it's not really cheap. And since we have a lot of games added every day, it's not really good to pre-calculate it. It's kind of complex. Yeah? So the logic is implemented once. We do not depend on any other department of the company pre-calculation. This is pure development. Yeah? So on the 3rd of February, we were really having an issue with this. So I mentioned the pages are pre-generated on the backend, and the response time for this call was around 100 milliseconds. So that's pretty bad. That means before you can even try to get the HTML for your page, you already have waited 100 milliseconds. You don't have the HTML, and of course, you haven't even sent it to the client. So this is really bad. So first thing we did was, OK, jump into that code and fix it. That's horrible. It cannot be that complex. Yeah? So we did. And then we got to the 60 milliseconds, which was pretty bad. So at some point, we decided we really needed to do something with it. Users were experiencing some pain, and we were trying to figure it out on the way. So I mentioned before that SpellGame used to be a huge LAMP stack as well, and we're moving all of that towards the Erlang stack that I showed in the beginning. So when you go increasing the traffic, and now we have like 80% of our traffic on that stack, you figure things out, basically. So you can stress test, you can do whatever you want. All is very nice, all is very useful, you learn a lot, but when you actually put it to real users, you figure out things that you had never thought about. So in the middle of this process, we figured out that 60 milliseconds was really, really bad, and we needed to do something with it. So we implemented Earl Cache, and that was around the 7th of February. And then the latency went down to below 20 milliseconds, which was, OK, not great, but OK, better, clearly better. And then around the 18th, 19th of February, we finally found out cool parameters for the eviction type and the validity time. We extended the validity, or actually we reduced the validity to 15 minutes or so, and we extended the overdue to 24 hours. And that was actually pretty good. So during 24 hours, the data auto-refreshes, except if there is an error, and then it gets kicked out and gets recalculated again. And the latency went down, as you can see, to 2 milliseconds, 3, 4. That was actually pretty good coming from 100. In the meantime, this service game application was actually responsible for running that code. And this graph can show you the memory usage. So what happened here? This is a very funny story. So the 7th of February, we were having 100 milliseconds response times, and the service game was consuming a little bit more than a gigabyte of memory. And then memory started going up. And if you remember, the 7th of February was actually when we introduced the cache. And that was a Wednesday. And we started measuring, OK, is this helping our users? Are things going better? And then we went into the 8th, the 9th, and the 9th was Friday. So OK, yeah, it seems to work. Should we clean it up? Well, Friday evening, should we? Should we? No, we shouldn't. Leave it like that. So nobody touched it. And on Monday, the 12th of February, we fixed eviction, which was obviously not working. Nothing was being evicted. So you can see 11 gigabytes of data being consumed. And then we fixed eviction, and the problem was gone. But that's not the coolest thing on this graph. The coolest thing on this graph is that if you see the memory before using the cache was actually twice as much as after using the cache, because we really had the service running on heavy resource starvation. So resources were running out, run queues were going up, complex algorithms were running all the time. Process couldn't finish their processing because they were stuck in the run queues, so memory was not being freed. And suddenly we started caching the data, and wow, all that thing went away. And the overload that we introduced by caching really wasn't that bad. And also you can infer already that the eviction is periodic because you can see the waves on the line. But you can even see that better in here. So this shows two different lines. The blue one is the amount of entries that are cached for that get-related labels call. And you can see that it oscillates depending on the time of the day. But the interesting thing to see is that every 5 hours, it drops. And that's a periodic eviction. Yeah? And the rest of the time, it goes up. And it goes around the 2,000 entries would be the average or something like that. That's the amount of information that we have cached. But the cool thing is the green line that follows is the hit ratio, which after the optimizations that I showed you the last couple of days when the latency dropped down to the 3 milliseconds, oscillates between the 96.5 and the 98.5 of hit ratio, which is really amazing. And that's just because we found, this is, again, not a universal solution, but this was great for a small data set with these variants of the keys. We have other calls, for example, for which we couldn't increase the validity for, or the overdue period for 24 hours, because the variance of the keys was huge. So it was kind of useless. It was just using more and more memory, and the heat ratio was not going up. But for this particular call, it really fit the bill. So to sum it up a little bit, lessons. If you need fine-grained memory control and a cache that survives restarts, and you want to do distributed caching maybe, Erl Memcache is a library that can seriously help you. If, on the other hand, you have a small data set and you want to use auto-refresh features, and you want to use this library to also cache business logic, so it needs error awareness, Erl Cache, yeah. It's not nice coming from me. I'm one of the main contributors to that repository, but I think it's a very cool library, honestly. And it could be better performance-wise, and it could be better in many other aspects, but it's really cool. It's very simple. And yeah, as you saw, this was a real crisis for us, and it was solved with that tiny little piece of code. So in the process, we have used several things from other people. So we used Poolboy for the worker pools in the Erl Memcache library. And to be honest, the binary protocol implementation for Memcache is not ours either. I can't remember the name, but it's in the README in the repo. You can actually find out the reference to the original author. We have used Lager for logging. And what we want to contribute to the community today are these three repos. So Erl Memcache, Erl Cache, and the last one is actually a piece of functionality that implements Python-like decorators for functions for Erlang. So you can write the macros on top of the functions, like I showed you, with a cache for the memoization. So go ahead, take a look. Feel free to use it. Particularly the third one, if there is any macro guru in the room, it could definitely use some cleanup. Yeah, that was it. So if you have any questions, now it's a great time to shoot. Yes?
So is the third library using a parse transform?
Yes. The question was, the third library is using a parse transform. The answer is yes. It uses a parse transformation to figure out the name of the function that needs to cache and the arguments, and basically hooking in runtime to know what should be used to auto-generate the key for caching and what the refresh callback should be. Yeah? What else?
What's the cost of your, like basically what do your tail latencies look like if you have a cache miss?
Sorry, come again?
If you have a cache miss on your systems,
A
cache miss, if you don't hit the cache.
Okay, a miss, sorry, yes.
Yeah. What do your latencies look like?
What?
What are your latencies?
Okay, so the latency is when we have a cache miss. There we go. Yeah. So latency when we got a cache miss is around, for this particular function, is around 60 milliseconds. But again, this is one of the most expensive calculations that we do in line. For more complex stat, we run it through our data warehouse department, who actually pre-calculates offline and populates a table. We just have to read. So basically, the idea is, if you wonder about the response times for HTTP requests in the gaming portals, yeah, I can tell you those are actually better than when we used to generate the page from the front end in the old stack, like way better. And something around, yeah, I don't want to lie to you, but probably anywhere in the world around the 3-second stops for a very complex page. Yeah. Serving from Amsterdam. More? Well, thanks a lot. Oh, wait, there's one more.
What happens when several processes call this function that adds cache?
When
yeah? You have a cache miss.
So the worst thing that can happen is that they all are doing it asynchronously. Yeah? So basically, they call the function, and the value is not found, and then the other appears while the calculation is being run, and the value is still not found for it, so you're doing the calculation twice. But basically, the last calculation will prevail and override. So if you set the same key twice, it doesn't really matter. So after you set it the second time, the validity is starting from that set operation. Yeah?
Could you remind me, the
And ETS tables, yes. So it's ETS tables with a read concurrency setting. This is also one of the reasons why this is better for small, not only small data sets, but particularly small entries. So I heard stories about a couple of gigabytes entries in ETS tables in certain companies. Yeah, this is not good for that, because every time you do a read, you're actually copying to the process space, so this is really bad. But yeah, from my professional experience, that's really not a common case. You shouldn't do that. No? Okay, thank you now.